All right, so in this video, we're just going to look at a handful of examples of power series. And so I can show you the sort of variety of different possibilities for, for example, whether the endpoints of the interval of convergence are included as, points where the series converges and so on. So the first example we'll look at is this series, n equals 0 to infinity of x to the n over n factorial, right? So here an is 1 over n factorial. So let's calculate the radius of convergence, right? Now, in the theorem we proved about the radius of convergence, we defined the radius of convergence as the reciprocal of the lim sup of, basically of the an, absolute value of an to the 1 over n, where we were using the root test, basically, right? But the thing is, in situations like this, you can apply the ratio test and you can actually get a result out of it, and then that can tell you what the radius of convergence is. So here, we'll say that, okay, notice that the lim, or the limit, I guess, actually, of n plus 1 over an equals the limit of 1 over n plus 1. If you just cancel off all the, here you have 1 over n plus 1 factorial, here you have n factorial, so when you, 1 over n factorial, so when you sort of, simplify that, you get n factorial over n plus 1 factorial, and then the n factorial cancels out with the, n plus 1 times n factorial in the denominator. So this is 0. So since this sequence not only has a, well, it has a limit specifically, right? Not only does it have a well-defined lim sup and lim inf, it actually has a limit, and the lim sup and lim, so that means the lim sup and lim inf are equal, right? So, and then what we know about, from I don't know if they actually, oh, right, corollary 12.3. So then by 12.3, we know that the lim sup of an to the 1 over n is 0, so r is plus infinity, right? Because so r is just supposed to be like 1 over this, and the convention, of course, is that if this is 0, then r is just plus infinity. So the series converges for x in r. For all x, the series converges. In fact, it converges. Oh, great. Please. Hey. I didn't say Siri. I said series. All right, anyway, it converges to e to the x. Right? This is the Taylor series of e to the x. You might be familiar from basic calculus. Yeah. So, okay, just, this is an example of also how you can actually use the ratio test to analyze a power series, even though the root test is sort of like how we define the radius of convergence. The ratio test can still be useful in situations, especially where the ratios actually approach, they actually have like a limit, and it's not some, range of values. Anyway, yeah, so that's the first example there. All right, let's look at the next one. So example 2 here is going to be just the series x to the n, which we already pretty much looked at, but just to sort of dot all our i's and cross our t's. In this case, an is 1 for all n. So we have the lim sup of an, the 1 over n is just 1. So r equals 1, right? So this means the interval of convergence, and the interval of convergence is just what we call the set of x where the series converges, right? We know it's an interval, and specifically we know it's an interval whose endpoints are plus or minus r, right? We just don't know whether it's open or closed at the two endpoints, okay? But in this case, it's something like, you know, I'm going to put sort of squiggly, or wait, I don't know, dotted lines or something, because we haven't checked the endpoints, so we don't know. But then you can check, and also I meant to say -1, 1. I don't know why I put r there. So -1, 1 at x equals -1. This series is just the sum of -1 to the n, which diverges. At x equals +1, this series is just the sum of 1, which also diverges, of course. So the interval of convergence is the open interval on both ends from -1 to 1. Okay? Okay. So yeah, if you took Math 1B, this might seem very familiar so far. All right, let's look at the next one. So example 3. The series 1 over n x to the n from n equals 1 to infinity in this case. Oh, that's funny. There's a typo in the book. They say it sums from 0 to infinity, but that's not quite allowed. No wonder. It doesn't matter. Anyway, so in this case, oh yeah, let me make this a little nicer. Okay, so in this case, an is 1 over n. So the limit of an to the 1 over n is 1, right? So beta equals 1. So the interval of convergence, oops. Oh, sorry, I guess r, you know, r is 1 over beta, but they're both 1 in this case. The interval of convergence is something like -1 to 1 again, right? But we have to check the endpoints again, right? So you all pretty much always have to check the endpoints. So when x is -1, the series is the sum of -1 to the n over n, which converges, right? Because it's alternating. It's an alternating series, right? The terms approach 0, the absolute values decrease, and the signs alternate, right? Those are sort of the three critical properties for it to converge as an alternating series, right? On the other hand, when x is 1, the series is just the sum of 1 over n, which is divergent. That's the harmonic series. So the interval of convergence is, in fact, oops, it's closed on that side, -1 to 1 open. Okay. So that's an example where the interval ends up being half open, half closed. And actually, usually, like, it's almost always like half open, half closed when, you know, when if the absolute value of x equals r, then but like the terms end up decreasing as like 1 over n basically, or something like that. Any series whose, like, if you take any series of positive terms where the terms approach 0 but the series still diverges, and then make that the series of coefficients, then you'll get something where there's like because when x becomes -1, it'll become like an alternating series. So you'll get a closed endpoint on one side. And if you make the coefficients themselves already be alternating, then it flips which side the closed endpoint is on. I think we'll see an example of that one too. Yeah, in a bit. Yeah, we'll see. We'll see one probably in the next video. So anyway, so that's that one. And then there's here's an example where the radius of convergence is finite, but the interval is closed on both sides. So this is the series 1 over n squared x to the n equals 1 to infinity. We start this one at n equals 0 too. Again, r equals 1, right? Because an to the 1 over n approaches 1 again. So r is 1. And then when x is 1, series 1 over n squared converges. When x is -1, the series -1 to the n over n squared also converges. So the interval of convergence is the closed interval -1 to 1, right? All right, last example for this video. Example 5. The series n factorial x, I need to just turn my phone off for these, x to the n from n equals 0 to infinity. Remember that 0 factorial equals 1. That's just a convention. It's good to be familiar with. Oh, that's also kind of important for the Taylor series of e to the x here, so that when n equals 0, the term is actually defined. Yeah, anyway. Yeah, so in this case, the limit of, let's see, right, the limit of an plus 1 over an is plus infinity. So the lim inf, well, I shouldn't underline that, it looks weird. I'm just emphasizing the lim inf of an plus 1 over an is plus infinity. So by 12.3 again, the lim inf of an to the 1 over n is also plus infinity. Okay, remember, 12.3 says the lim inf of an to the 1 over n is greater than or equal to the lim inf of an plus 1 over an. So if this one is plus infinity, then this one is also plus infinity, right? So, so that means that the lim sup is also plus infinity. So r equals 0, right? So the interval of convergence, quote unquote, is just the point 0, right? Because clearly it does converge for x equals 0 because every term is 0 except when n equals 0. So it converges to 1 at x equals 0, but it doesn't converge for any other value of x because basically n factorial just grows too fast. N factorial grows super exponentially, or hyper exponentially, however you want to say it, faster than any exponential function. So that's the problem. That's why it won't converge. And actually, that's kind of like, if you think about it, you could almost guess this just from what we know about example 1. If this converges everywhere, that also means that n factorial grows faster than any exponential function, right? Because no matter how big x is, n factorial ends up outrunning it so that this series can end up converging, right? So if we already took for granted that this series converged for every value of x, that like automatically would tell us that this series should diverge for all but x equals 0, okay? So anyway, those are the main examples that kind of go through all the different possibilities of what the interval can look like. We had an open interval for example 1, or no, we had all of R for example 1. We had an open interval for example 2. We had a half open interval for example 3. We had a closed interval for example 4. And then we had just a single point, a degenerate interval, if you want to call it that, for example 5. So you can kind of see what they look like. All right, so that's it for this video. We'll look at actually a couple more examples with slightly weirder series in the next video.